This video is about composition of functions. And for our notes, we'll just dive right in with the definition. The notation for composition is F, and then with this little circle character. Importantly, it's not a dot. A dot would indicate multiplication, which we've already seen multiplication of functions. This is different. It's called composition. The second and more useful way to write it is f of g of x. All right, so in the first notation, when you see f circle g, that actually is read as f of g. And it's easier to see it, I think, in the second way here, where you can actually see the g of x function is the input for the f function. And so this is called composition. Of course, composition means to put together or compose, and so you're putting one function inside the other. Also take note in the way this is defined that g is the second function seen in the first notation here, so f circle g, and that function, the second one, ends up as the inner function here. As we do algebraic work with this, we're going to have to be clear on that order as well. Now, the domain of a composition, in this case f of g of x, this can get a little complicated. It's the set of all x in the domain of the inner function. Okay, so there's a keyword inner. In this case, g is our inner function. It's the second one written, such that g of x is in the domain of the outer function. So again, we have to distinguish inner and outer functions. Now, we'll see this algebraically in a moment, but there is sometimes a helpful way to represent this with a picture, and I just want to review that here briefly before we try an example. So in a composition of functions like this, where we're composing one function with another, so a total of two functions, we have three different sets. Now, the first function, or the inner function, takes items from its domain, which we'll just put an x in that first domain. And then in this case, we're using g as the inner function, if you look at f of g of x in that order. So the first function takes something from its domain and drops it off as a g of x value in the second set. So we could call like a is the domain of g function, and it drops it off to set b. But then b becomes the domain of the second function. So in the way we've written this one, f, where the outer function is the second function, f is going to pick up the g of x value and drop it off as an f of g of x value. And so we could call that last set c. That would be the range of the f function. Now, if the picture is getting too cumbersome, you don't need it. It's just a good way to illustrate what's going on. The whole point of this overall domain of the composition function is that we only need to pick up values in A, the domain of G, that are going to make it all the way to C. Now, if we pick up something in A and it makes it to B, we just have to make sure F is going to pick it up to take it the rest of the way. So that's like the two pieces of this definition of domain we'll have to deal with here. Let's try an example where we let f of x be equal to 2 over x and g of x be equal to x over x plus 2. We want to find and simplify each of the following, including its domain. Alright, so first we want to find f composed with g. Well, practically we know that means f of g of x, which means g is the inner function and f is the outer function. Now, we're going to substitute these expressions together like we've been doing in previous contexts, wherein we're going to take the outer function, in this case it's the f function, and we're going to write that function but with a blank where we see the x. So instead of 2 over x, which is the original f function, we're going to write 2 over blank. I'm going to leave the blank a little large because in the blank we have to put the input, which is the other function, g of x. Now, g of x is defined as x over x plus 2, so that's what's going to go in the blank that we've left for the outer function. So really it's now 2 over x plus 2. It's a complex fraction, but it represents plugging the g function into the f function. Now we will simplify this. There's a little bit of flipping we can do to make this 2 times x plus 2 over x. If I just take this, or I'm dividing by a fraction, so I can flip that up and over and multiply by it. That would give us 2 times x plus 2 all over x. We could simplify by distributing the 2 and get 2x plus 4 over x, but that's about as good as it's going to get. Now, to find our domain, we have to consider the two pieces in our definition to put together. First of all, we need to figure out what is the inner function going to pick up from its domain. Well, the inner function in this case is the second one, right? That's g. The domain of the g function, as we can see by its definition here, this is a rational function, is anything that would not cause division by 0. Well, if x is negative 2, that's a problem because it would be dividing by 0, which means the domain of g means everything not including negative 2. So let's start making a list for our overall domain. We have to exclude negative 2 because the g function, the inner function, would not pick it up. But then we have to consider what is in the domain of the f function. Notice f, it has to exclude 0 from its domain, which means we don't just exclude 0 from the overall domain. If we go back to our picture, let me redraw a little bit over here. Remember our 3 sets in our picture? All right, so we know we have to exclude negative 2 because the g function will not pick that up. So we have to say can't use negative 2. But then the f function, our second one, we just recognize will not pick up 0 because 2 over 0 would not be defined. So we cannot use 0 in that domain. But we're talking about the x values starting way over in the domain of g, which means we want to know which x value over here in the domain of g would turn into 0 because we're not allowed to pick up 0 as we just discussed with the f function. Well, we can find that out by taking our g function, which is x over x plus 2, and setting it equal to 0. We know 0 is the problem that f won't pick up. So we're curious as to which value would g drop off as 0. So we're setting the g function equal to 0 and solving. That would mean, or in other words, x over x plus 2 does equal 0 when x is 0, but that's the only time. In other words, when x is 0, g of x would be 0, but then f of x would not pick that up. That means we're not going to use 0 in our domain either. So we have to exclude not only negative 2, but also exclude 0, because those two values are problematic. This means we'll summarize overall our domain as everything except negative 2 and 0, which would be negative infinity to negative 2, union negative 2 to 0, so we're hopping right over negative 2, but then we have to hop over 0 as well, so we'll union 0 to infinity. That's now everything except those two problem numbers as we just discovered. Let's consider a second example where actually the functions are defined the same. F of x is 2 over x, and g of x is x over x plus 2, but this time we want to find g of f of x and its domain. Notice the order of these functions is different from the first example. Now g is the first function and f is the second. That matters because that changes which function is the inner function. This now would read g of f of x, so we can see f is the inner function and g is the outer. So we'll write the outer function like we did last time, but this time it's g, the outer function, but with blanks. So instead of x over x plus 2, we'll write blank over blank plus 2, and in the blanks, for the input value, we're going to use f of x. So I'm going to write our inner function f in the blanks, so 2 over x is getting plugged into each of the blanks. So again, we have a complex fraction. This is 2 over x over 2 over x plus 2. Now we want to simplify this, and we can do so by using any method to simplify a complex fraction. We can try perhaps just multiplying by the minor LCD, which in this case would be the value x, or the variable x. If we multiply by x top and bottom, we'll end up with just a 2 on the top. These x's would cancel. And then down in the major denominator, we'll distribute the x and end up with 2 plus 2x. Now we could simplify this a little bit, and we can do so by factoring out a 2 from the denominator, so that we'd have 2 times 1 plus x, and then cancel the 2's, the 2 in the numerator and the factored out 2 from down below, so that overall our simplified composed function is 1 over 1 plus x. Notice that by reversing the order of the composition, we're still using the same functions f and g, but by reversing the order we get an entirely different outcome for the composition. Now we also still want to consider the domain of the composition, so let's kind of review our 3-set transfer that's happening. The inner function this time is f. F is going to pick up things from its domain, where we'll find the x values, and hopefully drop them off at the middle set where g will hopefully pick them up. So we have to ask first, what will f, the first function, not pick up? In other words, what's not in the domain of f? Well, if you look at the function f, it's 2 over x. That means we cannot divide by 0, which means x cannot be 0. So we have to exclude 0 because the first function, f, will not pick it up. It's not in the domain of the inner function. But then we have to consider, what would we have to exclude from the g function domain? And we look back at the g function and recall that when x is negative 2, we have a problem. The g function is undefined when x is negative 2. In other words, negative 2 is not in the domain of the outer function. Okay, well, we then have to ask, what value might f drop off as negative 2? And if we can find such value, then f should not even pick it up. So let's think through our f function, which reads 2 over x. We want to know, when does that equal negative 2? We're trying to avoid this. It turns out that if x were negative 1, then 2 over negative 1 is negative 2, which means if I were to try to pick up the value negative 1 with the f function, notice negative 1 is in the domain of f. It actually could pick it up. F just can't pick up 0. We've already excluded that. But if f goes ahead and picks up negative 1, then it will drop it off as negative 2, but g cannot pick that up. So that means we must exclude negative 1 as well. So not only exclude 0, we also must exclude negative 1. Therefore, we'll summarize our domain as the following. We want everything except 0 and negative 1, so we'll say from negative infinity to negative 1, union, hop right over it, so we're excluding it with parentheses. And we want negative 1 to 0, but then we want to hop over and exclude 0, but then go on forever from there. So this set in interval notation represents everything on the number line except negative 1 and 0. Let's consider our next example, where this time we're going to let f of x be 2 times the square root of x, and we're going to let g of x be x cubed minus 8. We want to find a couple things. First of all, we want to find the domain of f of g of x. Now, to find this domain, let's actually be clear and find the composition just to make sure we understand all of its parts. When I say f of g of x, we're plugging the g function inside the f function. That means we have 2 times the square root of x cubed minus 8. So there's our composed function. Now, the question wasn't really asking for that simplified result, but if it were, that would be it. What it's really asking for is the domain of this composed function. So let's recall how this all works together. And the map, I think, helps to tie all the pieces together. This time, our inner function is the g function. Our outer or second function is the f function. So the g is going to pick up certain x values and drop them off as g of x's, and then we're going to see if the f function will pick up those g of x's. Now, if you look at the g function, the inner function, we have to consider its domain. As you recall from the definition in the notes of this topic where we discussed the domain of a composition function, we said it's all values in the domain of the inner function. Well, that's the g function. You'll notice the g function being x cubed minus 8, that is a polynomial function with domain all real numbers. So we can use anything for the domain of g. We'll just put a smiley face there to represent all real numbers for now. Okay, and then, but we only want those such that g of x is in the domain of the f function. That's over here. Now we need to know what the domain of the f function is. If you look back, f was 2 square root of x. The domain of the f function then is that all of its inputs have to be greater than or equal to 0. So that means that x cubed minus 8, which are going to end up as the inputs for the f function, all those values, x cubed minus 8, those have to be greater than or equal to 0 so that when plugged into the f function, f will actually pick them up for the domain of that root. We can solve this inequality by, let's say, if we add 8 to both sides, we'll have x cubed is greater than or equal to 8. And then you could solve that either using the SPIT method or with a graphical assistance on a graphing calculator. And this would yield that x is greater than or equal to 2. Now, if that's the case, remember, this means that the g of x values, which we're dropping off so that f will pick them up, we need to drop off values that are positive or 0, and that's exactly what this inequality represents. So that means we have to make sure in our final domain that x is greater than or equal to negative 2. There was no restriction on the domain of g, as you may recall, so that means the only restriction we have is that the domain for our entire function would be 2 to infinity, that is, where x is greater than or equal to 2.